Albert Einstein once stated that pure mathematics is, in its way, the poetry of logical ideas. It is a universal language, one that describes the structure of the universe. Just like any language, understanding this poetry of nature requires not only understanding its rules, but learning how to wield them with creativity and insight. Today, we will explore some of the techniques that allow us to tackle some of the hardest problems in the context of introductory calculus, but they go far beyond that. Solving challenging math problems isn't about number crunching, it's about mastering an artistic thought process that makes us sculptors of logical ideas. Along the way, you'll learn not only how to unravel these challenges, but also build up your own ingenuity and confidence in mathematics. With that being said, let's dive in. Despite the large number of forms that difficult problems can manifest themselves in, they all can be attacked with the same problem-solving mindset and process. Let's look at what this method entails before examining it in the context of calculus problems such as related rates and optimization. Let's start simple. Step 1. Read the problem while taking careful note of important quantities relating to what the problem is asking you about. Examples include area, volume, time, distance, etc. Step 2. Draw a diagram. Many times, hard problems will deal with physical situations that can be hard to and fully grasp without a visual aid. A diagram will be sure to keep you on the right track and will be worth your time, even though it feels annoying to make one at times. Step 3. Define variables and add them to your diagram. Defining the right variables is key to solving the problem. Generally, one of your variables should represent your ultimate goal in the problem, which you should have identified earlier. The one slight exception to this rule is that in related rates problems, you don't want to create a variable that explicitly represents the rate of change of a quantity. Rather, it is usually much more helpful to create a variable that simply represents the target quantity itself, not its rate of change, and we'll see examples of this in a little bit. The rest of your variables should represent the quantities that affect the value of this target quantity. For example, if the problem concerns area, then we should have a variable representing that area, and also variables representing lengths that can be used to find that area, such as widths and heights. Or if we're dealing with time, then consider creating variables for distance and speed along with time. Continuing, we have step 4, writing equations that relate the variables that have been defined. Usually, one of these equations should relate the target quantity with the variables that affect it, while the other should reflect constraints on, or relationships between, the variables. These constraints may be stated in the problem, for example, in the case of a budget, or they may be implied due to the nature of the problem. These implied constraints are often the hardest to weed out, but with practice you can develop an eye for them. Often, these implied constraints are geometric, so be on the lookout for places where relations such as the Pythagorean theorem might apply. Your diagram is also fundamental in this step as it can help you determine these relationships and write equations for them. Next, we have step 5, substituting in the constraint equations into the main equation with the target quantity to get an equation with fewer variables, if possible. This is generally good practice as it often simplifies matters in related rates problems and is crucial in optimization, but there are some cases in which there are no additional equations other than the main equation, and thus this step is not needed. At this point, how we proceed varies slightly depending on what type of problem we are tackling. Step 6 is to perform problem-specific steps to find the desired answer. Note that this is when the actual calculus part of the problem starts, at step 6. Don't worry about calculus until you get to this step. In fact, this is probably the most formulaic step in this whole process, so if you manage to get to this part successfully, you should be in good shape. Use techniques such as the closed interval method for optimization, while instead take the derivative and solve for the desired rate in the related rates. Finally, after all of that, we reach step 7, express your final answer in the context of the problem. I know that was a lot of information, but the best way to learn this process is to take a look at it in action. Let's look at some examples to demonstrate the use of this step-by-step method. In fact, I am mainly going to concentrate on steps 1 through 5, because these are often the hardest, and after completing these parts, the rest of the problem is mostly a computational exercise, one that is important to know how to do, but is comparatively simple. Instead, I'll present you with a few tips along the way that should help us reach a stage where we can just grind through the math to help us get the answer. If you do want to know any of the precise answers to any of the problems in this video, you can solve them and check the video description afterwards. With that being said, let's get right into it. Consider the following situation. A rectangle is inscribed within an ellipse with semi-major axis of a meters and a semi-minor axis of b meters. The length of the side of this rectangle parallel to the semi-major axis is k times 2a meters, where 0 is less than k, which is less than 1. If the semi-major axis of this ellipse begins growing at a rate of r meters per second, and the semi-minor axis begins growing at a rate of s meters per second, what is the initial rate of change of the area of the rectangle? Let's start from the beginning and notice what are the important quantities to focus on in the problem. Looking at the basics first, we are dealing with a rectangle inscribed in an ellipse, which means that the rectangle is drawn with vertices on the ellipse. The dimensions of the ellipse are probably important, and so is the stuff about k. Also, we will probably need to use the stuff about the rate of change of the axes of the ellipse as well, as our final goal is the rate of change of the area of the rectangle. The next thing to do is to draw a diagram to organize what all these words are saying in a more understandable format. First, let's add in our ellipse. Now, let's draw a rectangle. Each of its vertices lie on the ellipse. It's usually a good idea to label important lengths on our diagram. Let's add in the facts we know about the dimensions of the ellipse and that one of the sides of this rectangle has a length of k times 2a. Now that we have a basic setup for our diagram, we proceed to step 3, defining variables and adding them to our diagram. Since the area of the rectangle is an important part of this problem, it seems like a good idea to define a variable that relates to the height of this rectangle, as we haven't done so already. Let's call the height of this rectangle h and add it to our diagram. Onwards to step 4. The easiest relation to write down is that the area A of this rectangle is the product of its width and height, or 2kah. However, it would be nice if we could find a different expression for h, because right now we know nothing about it. Luckily, there is a way to relate h to other known quantities. It requires us to define a coordinate system for this problem, and this is a technique that can be very powerful in problems relating to figures that we know how to graph on an xy plane, such as ellipses here. In other problems, this technique can also work with circles. Usually, it's a good idea to define it in a way such that the math is as simple as possible, which generally means placing the origin at the center of one of the main figures in this problem, in this case, the ellipse. This is what I've done here. The benefit of doing this is that now we can note that this point on the rectangle is located at ka, h by 2 by the geometry of the figure, and it also lies on the ellipse. Thus, if we can write the equation for the ellipse, we can use it to find out what should be the value of y at x equals ka, and that should also be the value of h by 2. Noting that the ellipse has a semi-major axis of a and a semi-minor axis of b, we use our pre-calculus knowledge to write the equation of the ellipse as follows. Solving for y, we get the following equation. We took the positive solution of the square root as the point we are considering is above the x-axis. Evaluating y at x equals ka, we find that h over 2 equals b times the square root of 1 minus k squared after a quick simplification. Solving for h by doubling both sides of the equation, we get this resulting expression. This expression can then be substituted back into our area expression to get an expression for the area of the rectangle only in terms of quantities that were given in the problem. This is precisely what we need to solve the problem. From here, it's just some standard take the derivative of both sides and substitution to get the final answer, which I'm sure you're all capable of doing, and I'll let you do yourself if you so choose. The main takeaway from this problem, however, should be the power of defining a coordinate system in certain problems. Consider how general this technique is, because if I change the problem to ask for the maximum area of the ellipse, I could use the same method to get the same equation. With that now in mind, let's examine some more slick techniques with the next problem. This time around, I have a much simpler problem statement for you all. The question is to find the area of the largest isosceles triangle that can be inscribed in a circle of radius r. We repeat step 1 once again and highlight important information in the problem. We now complete step 2, drawing a diagram. We make ourselves a circle and then draw an isosceles triangle inside it. Technically, we don't know if the maximizing triangle is of this precise shape. It could be thicker like this, or thinner like this. However, the specifics about how we draw a diagram is irrelevant as long as we don't make any unreasonable assumptions. Proceeding, we must now set up some variables for this problem. It's not immediately clear though where to start, as we've been given very little information. In such cases, it can sometimes be helpful to complete our problem-solving method in a non-linear fashion and use later steps to help us with the previous ones. Let me demonstrate. We know from step 1 that we will need to deal with the important quantity of the area of this isosceles triangle. The simplest way to find area is 1/2 base times height, so it makes sense to define variables for area, base, and height to write the following equation. This is a bit like using step 4, which is about writing equations, in conjunction with our end goal to help us define variables. We can then label these quantities on our diagram. Note that doing so for the height requires drawing an additional line segment here. Now, unfortunately, we run into a new problem. We have this equation for area, but if we're going to maximize it, we need it to be in terms of only one variable, while right now there are two. We must thus develop a way to either express base as a function of height, or vice versa, or express base and height both in terms of another third variable. The key to doing this lies in strategically adding to our diagram from before. Learning how to do this is often an important problem-solving skill because with many problems of geometric basis, whether or not you are successful in solving them is dependent on what you add to your diagram to help you along the way. So, what line should we draw? Well, knowing precisely what to do is often a matter of practice and sometimes trial and error, but I'll give you a couple of recommendations. First of all, whenever you see a circle in a problem, always mark its center, like so. Next, it is often a good idea to draw radii from the center of the circle to points of interest. In this case, the three most interesting points on our diagram, other than the center of the circle, are the 3 points that form our triangle. Thus, we draw 3 radii to these 3 different points. Doing so gives us a bunch of new lines that we can now label. We know from the problem that the circle has a radius of r, so all the newly added lines have this length. You're probably wondering, how does this exactly help us? Well, the benefit of doing this is that now we're going to notice something interesting. We know that this angle over here is right, as the orange vertical line is part of the altitude of the triangle. This means that our additional drawing has created the following right triangle. This is important, as right triangles allow us to bring in the Pythagorean theorem into problems as another equation, so always be on the lookout for them. With right triangles, it's also good to define variables for their sides. We can label the vertical height of the right triangle as x. The horizontal leg of this right triangle is half of b, due to the symmetry of the isosceles triangle. We can now use the Pythagorean theorem to express b in terms of x and the constant r. We write the equation below. Then we can solve this for b and we get this equation. Next, we notice that the vertical height of the triangle h can be written as r plus x from a diagram. With that, we've now expressed both b and h in terms of the variable x, and we can substitute these equations back into our main area equation. This can then be quickly simplified by canceling the factor of 1/2 with that of 2 to get us a little nicer equation. At this point, we have just the kind of equation that we need to solve this problem, and we just need to complete optimization techniques such as taking the derivative and using the closed interval method to get our final answer. I'll leave that as an exercise to you all, as the main takeaways from these problems should be more about how we solve them or go into a position to solve them, as these are more nuanced bits. The key points here were the diagramming strategies that are invaluable when tackling a circle-related problems and the usefulness of looking for right triangles to use the Pythagorean theorem on. Let's look at one more example to see just a couple additional little techniques that can help us. We will follow the trend of deceptively simple problem statements with this one. A sphere of radius r is inscribed within a cone. Find the minimum possible volume of the cone. Similar to last time, the main information we are given is the radius of an object, this time it being a sphere. But it also is important to keep track of the types of polyhedra involved and to remember to minimize a volume. Now we have to draw a diagram, but we run into a little bit of a problem. This problem involves 3D geometry, which makes it hard to draw a diagram of what is actually going on. You could try your best to make a sketch that tries to resemble this situation, with a sphere inside a cone. But what is actually more helpful is to not worry as much about the 3D diagram, although you can make one if it helps you visualize the situation, but instead consider a cross-section of our 3D situation to create a 2D diagram. Almost all 3D geometry problems can be simplified in this way by taking a cross-section that reduces them to 2D. However, there are many possible cross-sections that we could take. We could take one like this. Or like this. And there are many other possibilities as well. That being said, there is one cross-section that is better than the others. It is this one, that goes straight through the axis of the cone and the center of the sphere. This is a general rule of thumb. It is often best to take cross-sections of things like cones and cylinders through their axes, while for spheres, it's good to cut through their centers. When dealing with multiple different types of 3D figures, we try to hit on as many of these general principles as we can, like we did here. If we depict this cross-section two-dimensionally, we get something that looks like so. As a result of using this technique, we now have a simpler diagram to work with. Recalling some of the information in our problem statement, we can begin to add to our picture. That being said, we again don't have a lot to go off of other than the radius of the sphere. However, we can supplement our diagram by doing some of the things that we did last time around. We add in the center of the circle and then draw radii to the points of interest, which in this case are points of tangency that result from the inscribed constraint given in the problem. Further, we will do another thing that we did last problem as well, but make it a little bit more explicit here. We will draw the altitude of this isosceles triangle formed by the cross-section of the cone. It is usually a good idea to draw the heights of isosceles triangles like this, as doing so allows us to make use of the symmetry of the shape, and creates a right angle that we can use later. We can now label some lengths. Each of these radii can be labeled as r in accordance to what was said in the problem. However, where are we actually going with this? Well, we want to remember that what we are looking for is the smallest possible volume of the cone, where the volume is given by 1/3 pi big R squared times h, where big R is the radius of the cone and h is its height. We can add these new variables to our diagram. Once more, we're going to need to express h and big R in terms of the same quantity to minimize this volume. To do this, we will need to use some geometric relationships. Let's begin by noticing how since this radius goes to the point of tangency with the triangle, it forms a right angle here. This right angle is part of this bigger right triangle over here. Further, we can see this triangle has a hypotenuse of h minus r. Now, we need to look at our diagram carefully and realize that this small triangle is actually similar to this larger triangle here that is half of this isosceles triangle. Why? Well, it's because they both have a right angle and share this angle up here. So by angle-angle similarity, they are similar. Finding these similar triangles can be difficult, as they can be hidden really well, but they are often key to solving many problems. Continuing, we aim to write an equation based on the corresponding side lengths of these triangles. But before we do that, we must first find one more length to get two pairs of corresponding side lengths between both triangles. We will find the hypotenuse of this larger triangle. Using the Pythagorean theorem on it and the fact that it has leg lengths of big R and h, we find its hypotenuse to be as follows. I wrote it on the other side of the triangle because our diagram was getting a bit cluttered. But know that the large similar triangle has a hypotenuse of the same length due to the symmetry of the figure. We can now go on and write an equation. In particular, these similar triangles allow us to write this relationship using the lengths that we know and the fact that the ratio of the short side to the hypotenuse of each triangle is the same. After some mildly messy algebra that I'll spare you from, we find an equation that gives big R squared in terms of h and the constant little r. If we substitute this back into our main volume equation, we get the following, which gives us volume only in terms of h and constants. Just like that, we have once again reduced a difficult problem down to a simple computational exercise in optimization with this equation. If you want to, feel free to go ahead and actually find this minimal volume. But again, the main takeaway from all these problems should be the methods we use to tackle them. Besides, problem solving is something one slowly gets better at over time, as we become exposed to new problems and learn to use the strategies from past problems on future ones that appear similar. Here's a list of all the little tips and techniques that we explored today. Don't hesitate to pause the video if you want to look over them once again. With that, we shall now conclude our review of problem-solving strategies. If you want to check your work and get precise answers to any of the problems in the video, look in the video description. Nevertheless, thank you so much for watching this video. If you enjoyed it, please consider subscribing and go check out my other videos for more interesting math content. I'll see you all next time.